In terms of quantum algorithms, it has been an integral part of the implementation that we have been discussing, and in most of these cases with unitary gates, we have shown the construction of new algorithms that can operate on fundamentally new principles. Generally speaking, the most famous of the ones that we have often used in terms of implementation has been the Shor's algorithm and the Grover's unstructured search algorithm, both of which have been featured as the most important algorithms to be implemented in terms of quantum computing. Although one of the first ones we often have managed to show in terms of implementation for the rudimentary computation has been the Deutsch-Joshua algorithm. So, algorithms have played a major role in the development of the or actually in the way that the implementation is appropriately working or not. That is sort of like a checkpoint also in terms of the quantum computer. In terms of the quantum computer implementation, quantum algorithms have in fact played a major role in proving that the quantum computation is properly working. Many problems related to the structures of the algorithms have also been looked into as the developments for the implementations have been taken care. The basic logic behind almost all algorithms have been in terms of producing superpositions of all possible values of a function and then using interference to reinforce the probability of desired solutions while suppressing the incorrect answers. Finding new algorithms has been a very difficult task and open problem in the field. However, the algorithms by themselves have often acted as a checkpoint for us to make sure that our implementation of quantum computing is going in the right direction. So, it also has played a very important role. As we know, the evolution of the theory seems to be quite simple. You have a certain set of the states that we are looking into in terms of the quantum states, which are digital and have their proper values encoded in terms of being in a particular state A or in terms of being in particular state B, and in simple procedures the detection or the measurement procedure just involves finding out how many are on what kind of state. So, in some sense the schematic picture of an information processing can be very simple in theory. So, it is in analogy to the digital communication network, it could be thought about as streams of information in terms of quantum states of a particular kind, in this particular case being A or B, or in between whatever their property B is being transmitted, and the counter is going to finally just measure it. In practicality, however, the typical picture of quantum information experiment can be as complicated as this. This is one of the optical approaches and a photo of an actual laboratory which works on optical approaches to quantum information processing. So, the photons are being counted and the same principle, however, it is a real big complicacy in terms of the actual implementation in a laboratory. So, the reality of the implementation process is often quite much more involved than the theory. So, one of the most important properties when we have been discussing implementations has been the concept of the DiVincenzo criteria to be followed. In order to function as a quantum computer, a physical system must satisfy a number of stringent requirements. These were summarized by David DiVincenzo of IBM in a highly influential 1996 paper, and in terms of implementation we have always followed these criteria, and I list them here once more for clarity and making sure that we remember this, and that is the first one being the existence of qubits. So, identification and existence of qubits so that they can be made into the process, that is the first part. existence of qubits, division into subsystems. And the second part involves 1 and 2 bit unitary gate developments. The third one involves the initializability into a standard starting state for the system concerned. So, for example, if you have chosen a subsystem, say the iron trap system, then the first property of the iron trap is to make sure that it has the proper qubits available, which can be isolated into a proper subsystem. Then see that implementability of a few qubit unitary gates are designable and possible. Then the other most important part is the initialization into the standard starting state. Finally, the availability of measurable bits are extremely important, and the critical part of this entire process lies in the low intrinsic decoherence of this entire system. Otherwise, the computational process cannot be completed, and so it is important that all these criteria are taken care. In terms of the iron trap, we have discussed many cases in the earlier weeks. For example, the cadmium case, there was the two states which were separated by 14.53 gigahertz, the two spin states of the S2 half state, being one going down versus the other going up, are the ones which were used for the iron trap condition, and it is the superposition of these two states which created a single qubit, and depending on how they interacted with each other in terms of their when they were set up in the trap, it was essentially used as the iron trap qubit. We have also discussed about solid state quantum dots, where the defect would often be utilized as a way of doing quantum computing. So, in the at the contact point, say the Schottky contact point, there is a donor implant site which was utilized as a single atom picture, so that these gates could address them and be available for the operations to go on. So, here for example, this switching voltages and the measured gate changes were found out by changing as the upward sweep. It would track the process as you go upward versus downstream process, and both of them about in terms of 4 millisecond cycle, they kind of tracked opposite to each other as the system was undergoing these upstream versus downstream changes. The system essentially tracked each other in the way of doing this processing. So, there are approaches where the solid state quantum dots have also been utilized, and that is one of the places where implementation has been looked at. The other important implementation is also the idea of using the magnetic resonance force microscopy, which is an experimental technique to measure the spin of a single electron on a solid surface. Generally, in almost all these approaches, we have been using the spin of the electron as our approach. Mostly, we have been using the spin as a quantum number, which we have utilized for making the implementable quantum computing. So, in iron traps also it was the spin of the electron, whereas in terms of NMR it was the proton or the nuclear spin which was looked at. So, here is the concept of the NMR quantum computing, where the maximum number of qubits possible with that has been shown. So, it was the 7 qubit system, where this particular molecule was specially synthesized to have the access to all these number of qubits. So, the fluorine and the carbon essentially set the stage for the qubits, which could be coupled and entangled and utilized for doing Shor's algorithm. So, this was one of the cases where it was used for doing quantum computing, and this is by far the largest number of qubits which have been used in terms of liquid state NMR studies. It has now shifted to other areas of NMR which are also being attempted with certain levels of success. However, each of these cases have their difficulties, so more details of this have been addressed in earlier lectures. So this is just a revision in terms of looking back and showing that we have looked into all these different cases. The other models of quantum computation that has been important, which has been the idea of the cluster state quantum computing, where the qubits are prepared in a massive entangled state and the computation is done by a sequence of 1-bit measurements. Most of these require very low temperatures, and that is one of the principal requirements for most of the processes that we have looked at. Another area which is being pursued is the adiabatic quantum computing, where the qubits are prepared in the known ground state of a Hamiltonian, and the Hamiltonian is then slowly and continuously altered to become a new Hamiltonian, whose ground state represents the solution to a problem. Both of these are equivalent in power to the circuit model. I mean, the circuit model is the ones which are been discussed earlier, and we have been discussing the circuit model in most of our cases of implementable quantum computing. However, these are alternate ways of looking at the quantum computing, and they give a new way of looking for algorithms. One of the ideas of the adiabatic quantum computing with light was shown in one of the implementation lectures, where the property of the light was chosen to interact with the system, quantum system. In the particular case, it was state of a molecule in a beam chamber, and the state of the molecule was being addressed by the property of the light which was being provided, and that was used in an adiabatic manner to try to show that new ways of looking at quantum processing could be done, and gates could be devised in that manner. In fact, I think a C0 gate was shown to be implementable by this way. So there are ways of doing equivalent looks at quantum computing, and these have been all discussed. In terms of looking at as to how we stand in the current picture, the needed tools have been in principle demonstrated in many cases. The operations at the single atom level in terms of nanoscale manipulation and detections require a little more development so that it can do better work. In connection to the one of the most developed techniques, although not commercial yet, soon going to be commercial hopefully, is the ion trap, as we discussed, which also has the highest number of qubits currently in real terms of how this circuit picture we discuss. In other ways of looking at it, there are commercial approaches of the D wave, which has its own different approach of looking, that is not the same as this. But in this particular case of the ion traps, for instance, high fidelity of the operations and can also help a lot, and nanoscale metrology is a development that can also go ahead in this direction. And so we have been discussing of the physical implementation aspects, and we have shown scalable systems with well characterized qubits are the basic way how the research is going towards. The ability to initialize the state to a simple state is one of the important criteria to start with. These are all practical ways of restating, say, the DiVincenzo criteria. Long decoherence times, a universal set of quantum gates, qubit specific measurement capability, ability to interconvert stationary and flying qubits, and finally ability to faithfully transmit flying qubits between locations are very important in terms of finally getting quantum computing as well as quantum information processing to occur. The idea of having flying qubits and transmissions are critical to quantum information processing. Now, one of the things which is to be cleared up, because many times the advantage of the quantum computing in terms of its huge parallelism makes people feel that it's sort of like an analog continuous processing aspects, because when we try to explain the idea that it's all the possible states between say 0 and 1, which are the two conditions of a classical bit, is available when you do quantum computing, it sort of gives a picture, and maybe sometimes it's colloquially even put as a way of doing analog computing, which is not really the process. So that's what I would like to clarify, because this may be something which might be pictured by some of you. So we'd like to point out that the basic idea of quantum computing is not analog. It's definitely a digital process, because we are having discrete values, and unless and until, see, the basic point of the word quantum lies in discreteness. So if we ever make ourselves confused with the idea of having analog in synergy with quantum process, it will not work. It is true that the way ultimate results are coming, these power and the way things happen, it might look that there are continuous operations or continuous states which are available, but still each of them are supposed to have very individualistic discrete values. That is the basic idea. And what it does in the process is solves the Schrodinger equation, which is a linear equation governing quantities which are amplitudes that are not directly observable. And so that is the power of the computing. There is the process of looking and manipulating the amplitudes that are not directly observable, which gives rise to the main power of the computer. And this fact has put into the profound implications that we are been discussing all this time. So in some sense, one of the major aspects which led to the development of quantum computer, if you go back all the way, was in some sense popularized and recognized first by Feynman, where he pointed out the most important part of the problem, that is the quantum computation is the way to go for modeling of quantum systems, and that is to understand that no matter what we do, the quantum process that we are looking at is going to require in some sense the quantum computer to finally give the best results. So in the simplest possible case, when we are solving linear equations, we are looking at the condition where we are solving the energy of the problem. This is the bound condition, and we have the Hamiltonian, which is essentially nothing but a kinetic energy and a potential energy part in the simplest possible one electron or one dimensional model. This is the simplest possible Hamiltonian that we ever write, and this is partly the case which we first solve in terms of the particle in a box and those kinds of other basic issues that we have discussed. And each of the states that we talk about has discrete energies, and that is the reason to believe and understand that it is never going to be what we talk in terms of analog. And when we are looking at this process, we have essentially one particle giving rise to n equations, and that is one of the biggest issues to understand here, that if one particle gives rise to n equations, if we are going to look at L number of particles, we are in principle looking to solve n to the power L equations, and that definitely cannot be done by an analog computer. So it requires a quantum computer which can then go ahead and solve the problem. So this is what it is looking at, that in order to really solve the problem in terms of a large molecule, in terms of the way how Feynman proposed the problem, is that if one particle would require n equations, and obviously to solve large quantum systems, you would require a quantum computer, because that only has the power to solve n to the power L equations. So that is one of the basic points behind the idea of getting to quantum computers, even from the basic principle of understanding the level of levels that we would like to do. So There have been several applications, and the first part, as we mentioned, is the modeling of the quantum systems. And in recent years, pharmaceutical industries and nanoelectronics have often wanted or demanded this level of computation which are necessary, which are in terms of modeling quantum systems more and more accurately, where Feynman's prediction come into being, and it's soon necessary to get into that kind of a level. So, one of the other very important applications has been the factorization of large integer numbers, which was proposed by Peter Shor in 1994, which has been a very important point, because this could lead to breaking of the security currently used in terms of using large integer for encoding data. However, that same principle can be utilized for achieving quantum cryptography, which would then be making sure that the information is so secure that it can never be accessed by anybody else. In other words, it is like if the information is accessed, it is known that the information has been tampered with, and therefore the information can be considered to be invalid in that case. So, giving 100% security and cryptographic information transfer. On the other important aspect of development has been the search algorithm, because that is also a very important process, where getting the answer from a set of possibilities is a very important issue. Many a times we have problems where we know that the solution exists, it is just to find out where the solution is, and this can also have huge implementation in many industry and military areas. So, there is a lot of applications that is going to be important for this kind of processing. What we will do now is to close on this summary kind of a lecture that we have been putting together in terms of the applications in connection to the quantum processings that we have been discussing, and we will in the next lecture deal a little bit more into the concept of the quantum system a little bit more in detail, so that it relates to all the developments that we have been discussing in terms of implementations, which may become more clear as a result of that, and we will go ahead further with that. Thank you. See you next week.